Evaluating the limits of trigonometric functions requires some techniques. The following theorems establish the ground for finding the limits of trigonometric functions. Let's take a look at these theorems. If g and h are real-valued functions with the same domain, and the value of g of x is less than or equal to h of x for all x in the domain, then for some a, the limit of g of x as x tends to a is less than or equal to the limit of h of x as x tends to a. This is obvious from the figure shown. Now, we use the result of this theorem for another theorem, called the sandwich theorem. The sandwich theorem is highly useful in finding the limits of trigonometric functions otherwise tedious to analyze. The theorem states that let f, g, and h be real functions, such that f of x is less than or equal to g of x is less than or equal to h of x for all x in the common domain of definition. For some real number a, if the limit of f of x as x tends to a is equal to L is equal to the limit of h of x as x tends to a, then the limit of g of x as x tends to a is also equal to L. In the figure, the curves in black represent the functions f of x and h of x. The red curve represents the function g of x. At point A, the limit of the functions f of x, g of x, and h of x is supposed to be L. Now, we will find an important geometrical proof that can be helpful in finding the limits of various trigonometric functions. In this geometric proof, the measure of x is in radians. We will take a unit circle. OQ is a line equal to the length of the radius. We draw another line, OS, making an angle x radians with line OQ. Here x should lie between 0 and pi divided by 2. We will draw the chord as shown. Now, we will draw a perpendicular from point S onto line OQ. The meeting point is P. Next, we draw a line from Q and perpendicular to line OQ. Extend line OS to meet this perpendicular line at R. We will get a relation from the figure, which is shown here. Here, all the quantities are real numbers. Therefore, the expression takes this form. In triangle OPS, we have sin x is equal to SP divided by OS. Since the length of lines OQ and OS are equal to the length of the radius, we can replace OS with OQ in the denominator. Also from triangle OQR, we have tan x is equal to QR divided by OQ. Hence, QR is equal to tan x multiplied by OQ. We will substitute these two inputs in the relation. Since OQ is positive, the relation can be represented as shown. Since x lies between 0 and pi divided by 2, sin x is positive. Dividing throughout by sin x, we get the expression as shown. Taking reciprocals, we arrive at the expression shown. Here, we can see that the function sin x divided by x is sandwiched between cos x and 1. Here, we will see two important propositions that can be used in finding the limits of trigonometric functions. For the function sin x divided by x, we can use the sandwich theorem. We will use the relation shown. We will find the limit of each function in this relation. At 0, the limit of the function cos x is 1. The limit of the constant 1 is 1. Therefore, the expression takes this form. Therefore, according to the sandwich theorem, the limit of the function sin x divided by x is sandwiched between 1 and 1. Let's look at the second proposition. We will use some relations from trigonometry. We will rearrange the expression of the function as shown. As x tends to 0, x divided by 2 also tends to 0. Therefore, we can write the limit in the first expression as x divided by 2 tends to 0. By the sandwich theorem, the limit in the first function is equal to 1. The limit of the second function is obviously 0. Therefore, the second proposition is proved.